Hi everyone, welcome to this webinar on machine learning and mean-field games. So today we are very happy to have Bora Yongacoglu from University of Toronto. So Bora is a postdoc in the ECE department, and so today he's going to present his work on partially observed n-player mean-field games, connections to POMDPs, and subjective equilibrium. Thanks a lot for accepting to present, Bora, and feel free to start when you're ready.
Yeah, thank you so much for the invitation, Mathieu. It's a pleasure to participate in the seminar. It's a great seminar, and I'm very happy to share the stage with so many good researchers. Hopefully, I can contribute to that tradition. So today's work will be some work that I did with my PhD supervisors, Sardar and Grudal. The paper details are here at the bottom. At this point, it's still a preprint, but hopefully in a few weeks, it'll be on to the next stage and accepted where we sent it, but I guess that's to be seen. The subject of this talk is sort of the intersection of mean field games and multi-agent reinforcement learning. And I mean, we're all, this seminar being focused on mean field games, I guess I'll try to talk a little bit more about the multi-agent learning part of this. These things are obviously very closely connected through their focus on modeling multi-agent systems, but in many cases there are sort of thematic differences in what you study in mean field games and what you study in kind of other types of multi-agent reinforcement learning. So I've listed a few key points under each, and these things aren't strictly contradicting one another. But one thing I want to highlight is that in mean field games, we often study it from the point of view of symmetric policies. You have a representative agent, all the other agents face the same problem, and so we consider the situation in which all agents use kind of the same policy. Whereas in multi-agent reinforcement learning, oftentimes we start out of equilibrium and everybody will be using, perhaps distinct policies from one another. And so you have this situation in which you've got agents using heterogeneous policies. So this is going to be a major theme in today's talk, and I'll say more about this later. But first, I'll comment a little bit more on multi-agent reinforcement learning. So of course, there's more than one agent in the environment. But critically, as agents learn, they're going to change their policy, they're going to change their behavior. And as a result, each agent is going to face this sort of moving target problem, where the environment that a given individual is observing is going to give them different feedback data over time. Furthermore, there's this thing in multi-agent reinforcement learning where different agents will be seeing different relevant information about the game. I mean, this can take the various forms, but ultimately what that means is the feedback that I use for my learning algorithms will be distinct from the feedback that you use for your learning algorithm, even if we face pretty much the same problem. And as a result, this heterogeneous policy thing comes up again. So maybe a picture for us to keep in mind throughout this talk is this little cycle. It's a bit of an idealized cycle, but you can kind of use this to study lots of reinforcement learning algorithms in general. This doesn't have to be multi-agent, but basically the idea is you take a policy, you try it out for a while, you collect some feedback data, then you assess the policy, maybe using value function estimates or something like that. And then eventually you plug that stuff into a revision process of some type, and then you get your next policy. So I'll give you some pseudocode to suggest what this might look like in a particular case, but this is this is the basic picture I want to have in mind, the play, assess, revise cycle, as we'll call it. So a bit more on multi-agent learning. A lot of the time, I've encountered people studying this in the context of Markov games, where that generalizes MDPs to multiple agents. But it has sort of a downside for modeling large-scale systems, which is that typically we assume that the state variable is observed by all agents. So in the world of multi-agent reinforcement learning in Markov games, there's a couple of sort of paradigms that I care about in particular. One of them is what we're going to call independent learning in this talk, and I'll say a lot more about that in just a second. And the other one is what we call win state lose shift algorithms. This is using some language of other researchers. So when I say independent learning, the thing that you can basically think of is that each agent is going to discount the role of strategic interaction, and they're going to kind of pretend like they face a single agent reinforcement learning problem. They might know that they have other agents in the system with them. They might not know. In any case, they're going to behave as if they're facing a single agent problem. And in the literature, you'll find lots of rationales to explain why you might take this approach. And a lot of the time, these rationales kind of seem like they're well in line with mean field theory. Okay. So I'll come back to that, but yeah, so here's a few bullets in case you just want to take a look at that. The second paradigm that I wanted to talk about was this thing of win-stay lose-shift algorithms. So remember that flow chart I gave with the play, revise, and assess, excuse me, play, assess, and revise cycle. This is just some pseudocode to kind of suggest the same thing. So for each player, they're going to start with some policy. So player I will start with pi I 0. They'll play using that policy. It may be at time period k. They'll play with policy pi I k. They'll try to assess how good that policy is. And then depending on whether they're happy or not with the outcome, they'll either keep their old policy or they'll try something different. So I've colored it green to say, if I'm happy in the sense that I'm satisfied, my policy has surpassed a certain threshold criteria of quality, then I keep my old policy and I choose it to be the same as the last one. Otherwise, somehow I'll change it. Maybe I randomly update it, or maybe I have a direction of changing my parameters so that I'm improving my expected reward or something like that. This is kind of a broad thing, and it's been used in many settings. It takes different forms, but anything that looks like that, I'm going to call win, stay, lose, shift, and the name tells you basically all you need to know about it. So those are the two paradigms that I'm interested in. And now throughout the rest of the talk, we're about to start into the actual technical details. If you ever wonder, oh, why is he coming at this from this point of view? The questions that I guess I was interested in at the beginning of this research were informed by previous research that we did in Markov games, where I guess as our foundational tenet, we said the play will start out of equilibrium, and then each player will kind of revise their own policy in this way that we've just described. What happens to the joint policy process as time goes by? Will it converge to something? How does it depend on the structure of the game? How does it depend on the initial policy and that kind of thing? So we started out doing this kind of thing in Markov games, and we found some nice results for two-player games, but also for n-player symmetric games. And that kind of is how we got into mean field games. So more on this in a little bit. So here are some teasers for what I hope to convince you of by the end of the talk. The first is kind of a little bit facetious. It's that we should write x mu a instead of x a mu. This isn't a very serious point, but I guess you'll see what I mean when I say this at the end. The second point is actually probably where a lot more of the originality of this work lies. And it is that if each player starts this policy revision process out of equilibrium, and each player only has partial observability of some game relevant information, then we might end up at surprising joint policies. Okay, and these things might be asymmetric, and so it might be good to come up with new solution concepts to understand why we arrived where we did. Okay, so that's the high level stuff, and now I'm going to start into the technical stuff with symbols and so on. If there's any questions in this next section about symbols or the setup, please feel free to interrupt or post a question into the chat. So this is going to be an n-player model for mean field games. In that sense, it's going to be a little bit non-standard. And there's going to be a few objects that are either a little unusual or, they make something explicit that is usually understood. So the first few things are pretty standard. One of them is that, we've got this set of players, which I'll denote by n. We've got finite state space, observation set, and action set. So I guess the observation set is sometimes implicit, but I'm going to denote it by y, and I'll leave it vague for now, and I'll tell you about it more in a second. We've got this thing phi I, which is going to be player i's observation function. And what this thing does is it receives an n tuple of states, and it'll tell player I some observation about the rest of the system states. So I'll introduce more terminology in just a second. We've got a cost function, and this cost function C will take a state, a distribution, and an action, and it'll spit out a real number. We got this transition kernel ploc for local. And what this does is you give me a state, distribution, and an action, and then ploc will give me back a probability distribution over the states. Finally, I've got my discount factor and some initial distribution. That initial distribution is going to act on n tuples of local states, or excuse me, global states. I might have said that. I added too many details on what I said out loud. But okay, so the flow of play looks like this. At a given time, player i's local state will denote that by xit, and that belongs to the first set x. But then I'm going to use a bold letter to denote n tuples of these things. So with one entry per player, and I'm going to call that thing a global state. So a global state is made up of each player's local state. There's going to be this thing that I'm either going to call the mean field or the mean field state, or maybe the empirical distribution or something like that. And this is kind of what you expect it to be. It's a probability distribution that assigns mass mu t to some set B. Sorry, it assigns a mass to each subset of local states, and then that mass is just going to be the proportion of players whose local state is in B, for instance. Player I will then see some reading of the global state, and it won't necessarily see the whole global state. So this is the partial observability part of the title. I'm going to see xt, but I'm only going to see it through varphi, this function. After I see all this information, I'll pick an action. I'll incur a cost, and I'm going to see the cost CIT at time t, but I won't necessarily see the actions. Actually, sorry. I don't necessarily know the function c that produced it. So a priori, I might not know that. After all these things, the player will incur a local state transition, and then this process will repeat again at the next time. So some quick remarks on notation. I'll use I, usually maybe j in the player superscript. Time and iteration indices will go into the subscript. Here are my standard choices for random variables. And then if I want to talk about a state and then it won't be a random variable that actually gets played during the course of play, I'll use s instead of x. So that'll usually be the distinguishing thing I do. Oh, and of course, minus I means every player except for player I. So I'm going to talk about an n-1 tuple of things where player i's part was removed from the n tuple.
Sorry, Bora, can I ask a quick question? Could you repeat what is the distinction between s and x, please?
Yeah, so like x will be like a random variable that like in the course of play, this will be the random variable that's selected. And then if I want to say, x, this bold xt equals to a particular value, I'll usually use s to be that particular value. Just to try to distinguish. I might be inconsistent about this, so please excuse me if I am.
No, no worries. Thanks.
Yeah, so for instance, here s is just some generic element of xn. So I told you about this thing mu t, which was a random variable before. That was the empirical distribution that we encountered at time t. In order to keep track of that, it'll be helpful for us to make this function mu, which this mu is sort of more upright. I don't know if that really comes across in the slides. But this thing is a function that takes n tuples of states and then tells you the empirical distribution associated with that global state. Okay, so you get a whole lot of parentheses here, unfortunately, because this thing, mu s, is actually a probability distribution. But with this notation, I'm going to define this thing emp subscript n. This is the set of probability distributions that can be made as the convex combination of n atoms, or I guess with n atoms. So this set emp n is a finite set. It's the image of this mu under the finite set x, x to the n. So I hope that's kind of clear. And then with this notation, the random variable mu t is simply the random variable xt fed into the function mu. And then we know that mu t now takes values in a finite set. Okay. So the next part is where the first, I guess, departure from standard modeling happens, which is this thing about the observation channel. So we have this set y, and then we have a collection of observation functions, as we're calling them. And then jointly, I'm going to call this pair the observation channel for a game. And I've left it vague what y is up till this point. But now I can kind of specify some alternatives that we might want to consider, depending on our setting. So the first of these is global observability. In this case, my observation set is simply n tuples of strategies, n tuples of local states, in which case there's some underlying state, and then my observation of that would simply be the whole system global state. So this one is way too much information to really be reasonable in a large scale system, but it's probably a good sanity check for making sense of our theory. The second one is, I guess, much more reasonable for modeling mean field games. And I'm going to call this mean field observability. In this case, my observation set is my local state space cross the set of empirical measures on n atoms. Okay. My observation function at a given global state, this bold S, it'll tell me my component, SI, as well as the empirical distribution associated with the global state. That's all I get to see. So I don't get to see Mathieu's local state. I don't get to see anybody else's local state, for instance. The third is going to be a generalization of mean field observability, in which case, instead of seeing the whole mean field distribution, uncompressed and kind of very informative, it might, in some settings, it might make sense to first compress that mean field distribution and then only get to see the value of the compression. So I'm going to take a function f, I'm going to pass my empirical distribution through f, and then that's going to be my reading of it. So I'll give you two examples. One would be something like this, where we have a navigation app on our phone, and I don't really know who it is that is on these red links, but I know that there's lots of congestion on these links. So relatively speaking, I know that this link has heavy congestion and this green link here has light congestion, but I don't know, what proportion of drivers are on each part of the road network. If you'd rather see that with symbols rather than a picture, imagine a state space that has, four states. And then suppose I'm in state 3, and then we know that there's this distribution. So there's 20% of people are in the first state, 20% are in the second state, 1% are in the third state, and 59% are in the fourth state. The reading that I might get instead of 0.2, 0.2, 0.01, 0.59 might be there's a moderate amount of people in states 1 and 2, a low amount in state 3, and a high amount in state 4. So this is what I mean when I'm talking about compressed observability. And then finally, a special case of compressed observability is when you throw out all that information about the mean field and you only see the local state. So those are the 4 observation channels that we consider in this game, or in this model. Are there any questions about that, especially about, I guess, the number 2, 3, and 4? Let's pause for a second. Okay. So why am I making such a big fuss over being explicit about the observation channel? Well, it's because the observation channel determines what each player gets to see and the local history available to that player. So the local history is important because my action selection can only depend on what I saw locally, and maybe a random number generator or something like that. So to make that explicit, player I is going to see this local history HIT, which consists of the history of my observations, the YIT sequence up to time t. I'll see my own actions up to time t-1, and I'll remember all the costs that I paid in the previous periods, and I don't see anything else. Okay, so I don't see the actions of the other players and so forth. That's going to define what set of policies are available to me, and then I'll denote player I's policy set by pi I. I'll denote the joint policy set by boldface pi. Once players specify what policies they're using, then we can look at our objective criteria, which is going to be expected gamma discounted cost. So I guess this part's pretty standard. Just the cost I pay at time t multiplied by gamma to the power t. So with all that specified, I can now define an optimality criteria, which is I'll give you 2. One will be epsilon best responding with respect to an initial distribution. And what that means is that, you fix the initial distribution on global states, in this case, nu. I need to achieve within epsilon of the infimum cost when the system is initialized with nu determining everybody's local state. A more stringent optimality condition is called uniform epsilon best responding. And it's when we epsilon best respond, the same way as above, but then uniformly for every initial distribution. So you can imagine the second one is harder than the first. A policy might not be good for every initial distribution, but it might be good for some.
Can I ask a quick question? Sorry to interrupt again.
Mm-hmm.
So well, I guess in both of them, but in particular in the second one, do you assume that the players observe or know the initial distribution, or it really depends on the observation channel?
Yeah, it's a good question, and I think we've kind of we've been agnostic about it. So I guess a policy could be uniformly epsilon best responding. But at this point, we haven't really made that clear in any of our work. Yeah.
Okay, I see. So do
Do
you
you
assume that players know new, for example, but after that maybe they don't observe the mean field, but still they know the initial one for sure?
Yeah, no, I guess in principle, yeah, but I guess
Okay.
practically it doesn't really show up in any of the deductions
Ah,
after
okay.
this. Yeah.
Okay.
So
Okay. I see.
was there kind of a follow-up? Maybe we could take the question to
Okay.
the end in case it becomes relevant.
Okay.
But
Sounds good.
yeah, it's a fair point, I guess. If you want to think of it that way, sure. Maybe that would be good just to make it concrete. Suppose the player knows new.
Okay. Okay. Thanks.
So yeah, important to mention because now the equilibrium definitions I'm going to give you are also going to involve these news. So for each of those optimality conditions, we'll have a corresponding solution concept. So epsilon equilibrium with respect to nu is going to be everybody is simultaneously epsilon best responding to one another with respect to nu as the initial condition. Whereas perfect epsilon equilibrium is going to be everybody's epsilon best responding to each other uniformly across initial conditions. So those are the two solution concepts. The second one is very strong, but useful. So what's the problem is that if I'm interested in studying a partially observed n player mean field game and I want to understand how to best respond to my counter players' policies, well, like the set of all policies available to player I is going to be huge. It's going to be, it's going to be full of these like policies that depend in a complicated way on history. And so it's going to make challenging analysis. It would be nice if we could justify it to be able to restrict our attention to a highly structured subset of policies. Of course, this might not be justifiable, but it would be nice if we could. So we'll start out talking about these things that I'll call them stationary policies in this talk, but really they're memoryless policies in the sense that they're only going to use the observation available to a player at a given time, and they're going to do it in a time invariant way. So player I is going to look at its current observation YIT, and it's going to throw away the rest of the history and then simply pick its action according to YIT, maybe random. Is this justified? Not necessarily. This is going to be kind of the point of the next section of the talk. But this happens a lot in multi-agent reinforcement learning algorithms anyway, so might as well start considering this sort of policy and what happens when agents use these sorts of policies. So a stationary policy, you can just think of it now as a transition kernel on actions given observations. So I see symbol YIT, and then I plug that into a transition kernel that gives me a probability distribution over my actions, and then I'll pick my action accordingly. So a policy is memoryless stationary if and only if there exists such a transition kernel. Again, I want to emphasize that at this point, we know that each player wants to minimize its gamma discounted costs, and it faces some arbitrary, some general, not necessarily MDP stochastic control problem. And so there is no reason a priori to think that best responses should be memoryless or something like that. Okay. However, if the game has global observability, there's a lot of really nice structure that comes from these memoryless stationary policies. We know that if the other players use a stationary counter policy, then player I will face an MDP. And from this, you can derive the fact that there exists some perfect equilibrium, a perfect zero equilibrium where everybody's fully best responding. That thing exists within the set of stationary memoryless policies. However, if we go from global observability to any of the other observation channels I just mentioned, in the case where n is finite, we know that this mean field distribution term, that thing is going to evolve randomly as opposed to deterministically. And so my costs and stuff are going to depend on some partially observed quantity that might evolve in a non-Markovian way. I mean, that'll definitely be the case, for instance, if the other players use complicated history-dependent policies. So the existence of equilibrium using sort of the argument of somebody like Fink in Markov games, you can't use those same arguments directly. And at least as of a few years ago, there was commentary saying that, yeah, this is relatively less understood. maybe let's contrast this with the standard approach to studying mean field games, where you go to the limit and you study a related model. In this case, the mean field flow evolves deterministically, and so players will face an MDP. It might be time varying, but it'll be an MDP. Okay. So in that case, I guess the stationarity part of memoryless policies won't hold, but then something else will hold, and you can use Markov policies or something like that. Okay, so I'm really going a little bit too slowly, so I should probably pick it up a bit. But if each player in a partially observed game treats its environment like it's facing an MDP, what will happen? Will the agents' learning iterates converge? If they do, how should we interpret these quantities? And then suppose that play gets stuck somewhere, is there a solution concept that kind of looks like perfect equilibrium that makes sense for understanding why play got stuck there? And then as a second point, if that like policy revision cycle that I described earlier is to be used, and players are going to do the assessment phase using sort of ill-justified learning algorithms, will play converge to a policy of some kind? So along the way, in trying to answer those questions, we kind of proved a few other things, and I'll talk about some of them briefly. So we connected our model to POMDPs and MDPs, and we identified a few cases where doing this is appropriate or inappropriate. And then we also proved the existence of perfect equilibrium under mean field observability. And then there's one result that I unfortunately won't be able to get to today. So I'll start with the kind of the results that we need in order to talk about subjectivity and so on. And the first of those has to do with connecting our partially observed n-player mean field game to POMDPs. This is going to kind of seem like, maybe a word of disclaimer, this is going to kind of seem like obvious stuff, but because n is finite and it's partially observed, I think this is somewhat outside of the standard mean field game stuff. So excuse me if it's a little if it seems a little obvious, but I'll try to talk about it just so we can justify everything that we do in the sequel. So when other players use some policy pi minus I, player I will face a POMDP if the global state process is a controlled Markov chain controlled by player I's action rather than the joint action. And then furthermore, if the dynamics of this global state process are homogeneous in time. So by the first of these, I just mean that, the conditional distribution of tomorrow's global state, conditioned on the entire history of the system and my action today, is the same as if I just knew today's global state and my action. The second of these, just I'm saying that this probability on the right-hand side up here, it should be the same across time. So, there's something that we can make this equal to for every t. So if both of those are true, then player I would face a POMDP. How do we go past this and then ask, well, does player I actually face an MDP of some kind? Well, in order for that to be the case, player I's observation would have to both summarize the cost-relevant history, and furthermore, it would have to satisfy this controlled Markov property using player I's local action. And it would have to do this kind of homogeneously in time. So those are the two things. Does player I face a POMDP? Does player I face an MDP? Fully observed. Sort of unsurprisingly, if everybody is using a stationary policy except for player I, then player I's control problem is basically equivalent to a POMDP. The hidden state is given by the global state. The observations are given by player I's observations. This is a bit unsurprising, so I won't spend any time on it. But to prove it, just condition on everybody else's joint action, and then use the product structure and so on. The more interesting question is, does player I face an MDP in this case? Okay, is my cost relevant part going to be, is my observation going to be cost relevant, and is it going to be satisfy this controlled Markov property? So the cost relevant part, I guess, it very clearly depends on the observation channel. Like if I have really poor information about the mean field term, then of course my observation variable won't be cost relevant. In the second case, though, if supposing I did have mean field observability, it's not immediate that this thing is a controlled Markov chain, and so we'll actually find that there are examples in which lots of sort of desirable conditions are met, and it still fails to be a controlled Markov chain. So in order to present these examples, I want to give a little bit of terminology. As we said before, memoryless stationary policies are these things. Mean field observability is when my observation variable is my local state in this empirical term. The third one is new. The third one says that a joint policy is symmetric if all the other players are basically using the same policy. Okay. And so it's going to turn out, and we'll get there in a few slides, that both mean field observability and symmetry are essential in order for player I to face an MVP. And if you relax either of these, then player I won't face an MVP anymore, at least in general. So into the question. Do we absolutely need a symmetry condition on everybody else's policy for player I to face an MVP? And what kind of observations are necessary in order for player I to face an MVP? So I'll first start with a short example to explain how symmetric policies are crucial. So consider this state transition diagram. In state 0, you don't really influence where you go next. All of these edges are just up to nature. With probability 1/2 minus epsilon, you go to state 1. With probability 1/2 minus epsilon, you go to state 2. And then with some small probability, you just come back to state 0. By contrast, in the other two states, 1 and 2, you have full autonomy over where you go next. You can either choose to return to your state, by playing the action corresponding to your state, or you can choose to go to the other one by playing the appropriate action. So this is a state transition diagram. I'm going to build the game on top of this. We're going to have 3 players, but it really could be any number of players. The states are going to be the ones that I just told you. The action set's going to match the state set. I'll assume mean field observability. So this is the best case scenario for observability. And now let's fix a player and let's look at this from his vantage point. So player I is the first player. Next, the blue player here, player J, their policy is going to be always to play the action corresponding to their state. So they're playing a stationary policy, a memoryless policy, that depends only on their local state. And they say, I'll always stay where I am. The orange player, K, will always choose action 2. So he'll always try to push himself to state 2. Okay, so these are the 2 players other than player I, and this is the 2 policies are what distinguishes them. So the blue guy always chooses to stay, the orange guy always chooses to go to state 2. So now suppose player I, our distinguished player, starts at state 0 and observes that the distribution of other players is, 1 here, 1 here, and 1 here. This is what player I can tell. What player I can't distinguish is which of these 2 pictures he lives in. Is he on the left or is he on the right? On the left, we have player J is at state 1, and on the right, we have that player J is at state 2. The significance of the difference is that player J always chooses to stay. So on the left picture, we know that tomorrow player J will still be at state 1. Whereas in the right picture, we know that player J will be in state 2 tomorrow, and player K will force his way to state 2 tomorrow. So the important thing here is that from player I's point of view, in the left picture, he knows that tomorrow there will be at least 1 person at state 1. But in the right picture, he knows that tomorrow there's a chance that there's nobody at state 1. Okay, so in symbols, this is what I was trying to say. Initially, I think that there's a positive probability that I was in that right picture. And so the likelihood that everybody ends up in state 2 tomorrow is positive. Okay. But if 2 periods in a row, I see that we're, the same observation comes up, that means today and tomorrow, this holds. You can kind of work your way through that. I don't want to spend too much time on it, unfortunately. So maybe if there's a question about this at the end, we can come back to it. But basically, in this example, we get that the controlled Markov property won't hold. Okay, and the actions of player I didn't even matter here, given that we started in state 0 where his action had no influence. So in this example, the takeaway is that if the policy is not symmetric, then even with global observability and stationary counter policies, player I doesn't face an MVP. So what happens if we do keep symmetry, but we throw out the observation channel assumption and we use something else? So very, very quickly, I'll try to run through this. But we have a second example that shows player I won't face an MVP if you get rid of the mean field observability. So start with some number of nodes, integers ordered, and randomly assign a starting place to each player. Doesn't matter if they're on the same node or whatever. I'm going to use x bar t to denote the mean of the empirical distribution rounded up to the nearest integer. And then the way that the state evolution is going to happen is that at time t plus 1, player I is either going to be sent to the maximum value, m, or player I is going to be sent to this x bar t, which is the mean of the empirical distribution rounded up. So in this case, we're going to make m equal to 10 to be concrete. But you flip a coin, and then you either get sent back to the mean of the distribution, or you get pushed all the way to the maximum of the support. So critically, because x bar is like defined as the roundup of the mean of the empirical distribution, and my next policy is always going to be at least x bar, it means that the x bar process is non-decreasing. So for a given individual, if his local state goes left, that tells me something about where x bar is. I know exactly where x bar is after that. It's it's either the value I'm at, or it's above the integer below me. And through some knowledge about x bar, I could tell you something about mu t. So that was the state stuff. We can build a game on top of this. I'll make my action set the set of empirical measures. I'll make the cost function basically, I'll define it in terms of the Euclidean distance between the actual mean field term and the guess that I had about what it was. And very importantly, I'm going to give each player local observability, so it only sees its own state. So as I said, in this case, we have a non-decreasing x bar sequence. So initially, if my state is 10, so like here, this is like the maximum value or whatever, and I ask, what's the probability that tomorrow my local state will be less than 4? Well, initially, this is positive because it's possible that the mean of the empirical distribution is like 2 or something. On the other hand, if you include some memory and you can see that, yeah, today I'm at 10, yesterday I was at 5, and the day before that I was at 10 again, well, that tells me that when I was sent back to 5, that for sure the empirical distribution was no less than, it was strictly bigger than 4. And if it's strictly bigger than 4, that means I can never be sent to some number smaller than 4 in the subsequent period. So here's another instance where adding memory changes the conditional probability in a meaningful way. So I really do have to pick up the pace here, but I've given you 2 examples now where player I doesn't face an MDP even when nice conditions are given. Okay, and the punchline is that if player I faces if player I is in a partially observed n player mean field game, if player I's counter players use a policy that is symmetric and stationary, and I have mean field observability, then I do face an MDP, and my state process is given by my observation process. So all of these things were crucial. If you're interested in the proof details, I'll only say 1 or 2 things about it. But basically, to prove it, start with this left-hand thing and then condition on the global state xt, and then everything kind of falls out in a convenient way. So again, this might seem a little obvious, but I think this is not strictly obvious because of the finiteness of the number of players. So why did I tell you all this stuff? It seems like a little bit off topic, going back to the subjectivity stuff. Well, the significance is that you can use this to prove the existence of a perfect equilibrium in the set of stationary policies, even with partial observability and n players. And so the way you do that is you're basically going to say, okay, so first of all, what is the significance? Everybody's using a stationary policy, and even still, everybody is uniformly best responding to one another. And that's true over the entire policy set. Like my optimality isn't with respect just to stationary policies. Okay. Now, because of the partial observability thing, I can't use, like you can't reduce it to an MDP and then invoke Kakutani's fixed point theorem or something like that. You can't do that for every joint policy in the stationary policies. But you can use that theorem I just showed you a minute ago and then argue along kind of like a subspace of symmetric policies, and then everything goes through. So why is this interesting? Well, it holds for any number of players. Like I don't have to take n to be large, and it holds for any epsilon, including 0. So this is going to show up now in the next section when we start talking about subjectivity. So the setup has taken an unfortunately long time, so this might have to be rushed a little bit. But remember that I'm interested in multi-agent reinforcement learning, okay? And so far, I've shown you this picture, and I've talked a little bit about it at a high level. But now I want to talk more about the role of information in the learning and assessing process, okay? So we've established the fact that when we're not in equilibrium and players are using asymmetric policies, or if there is real partial observability, then player I won't face an MDP in general. And so it's not necessarily justifiable to use MDP algorithms. So what happens if we do this independent learning thing and player I acts like it's facing an MDP anyway? Okay. So basically, what happens in a mean field game, in an n-player mean field game, when we try to take the representative agent approach, but we break some of the key assumptions that go into being able to take the representative agent approach in a justifiable way. So when I talk about subjectivity in this work and in this presentation, here's the picture to have in mind. Each player will either believe or pretend that it faces some MDP. It'll assume that its observation process is the Markovian state for that MDP. And so it'll assume that there exists some optimal state action value function Q star and a function J that tells its objective as a function of the observations. So up till now, you might say, well, these two bullets, there's nothing wrong with those. But the consequence of believing that you're in an MDP is that you actually think that this function Q and this function J can be learned iteratively. And that's not strictly true when you're not facing an MDP, not because these things can't be defined, but rather because the dynamic programming recursion is not going to hold, right? So the iterative part is going to be problematic. But anyway, if I believe that I face an MDP, it only stands to reason that I'm going to think that a policy is near optimal if it satisfies an equation of this form, an inequality of this form. Basically, the cost that I think I'm paying, if that's less than epsilon plus the minimum cost I think I could pay, then I think I'm epsilon optimal with this policy. I'll say more about this in 2 seconds, but if there's any questions, do interrupt, please. Now, if player I does face an MDP, this is perfectly reasonable. I should say that if I face an MDP in this game, it's going to depend on the policy that the other players are using. So to reflect that somewhere in the notation, I'm going to put the policy's name in the subscript of my action value function Q. Okay, so I'm pretending that I face an MDP, even if I might not. And then I'm going to engage in this value learning process. So at time t, I'll pick my action according to my policy. I'll observe the observation variable yit. And then I'm going to get a cost, CIT. The orange part says I'll update my counters. The blue part says I'll update my value function estimates. So let's expand those orange and blue parts out a little bit. It clutters the screen a bit, but I think all this stuff is familiar. So we've got counters that tell us how many times we've visited this particular state action or this particular state. And I'm using state loosely here because Y, of course, doesn't have to be a real state if player I is not facing MDP. But then you're going to do something that looks just like a Q factor update. Even if Y is in a state, you can still mechanically do this thing. And this J learning thing is just going to be basically compute the average cost that I've paid according to this policy, or something that looks like the average cost. Something that approximates the discounted cost. So is this procedure okay? This is sort of a low-level stuff. So remember, the question is, do these things converge? What does it depend on? Does it depend on the observation channel in an important way? What are the limiting values? And then how can I use this to kind of make a prediction about how the game will be played? So I'm going to tell you about the convergence of this thing. And in order to do that, I should tell you the assumptions I use. So a policy is going to be called soft if it gives positive probability to each action given each observation symbol. And then one assumption I'm going to make basically throughout this talk is that if everybody is using a soft policy, then the underlying global state process is going to be irreducible and aperiodic. So assumption A1 here, this is necessary so that each global state is visited infinitely often. And you can imagine that's kind of important for your iterates being updated sufficiently many times. Okay, so this is a short form of what we've called Theorem 13 in the archived version of our paper. And it says that if players use a soft joint policy that is memoryless and stationary, and if assumption A1 holds, then using these value iteration algorithms, mixing up my language and I'm getting ahead of myself a little bit. If each player uses the algorithm that I just showed you, then there exist two functions, v and w, to which my iterates will converge. And moreover, if I have mean field observability and the other players are using a symmetric policy, then it converges to what we hope it converges to, basically the value function for my policy and the action value function for my policy. Critically, though, one of my questions was, how does this depend on the observation channel? And it turns out this convergence happens even more generally than this second point. So even if I'm dealing with partial observability, like true partial observability with compressed observability or local observability, this convergence will still happen, okay? And this is not based on MDP theory, but on POMDP theory. So here's a paper by some colleagues that might be of some interest to you. So this is a theorem statement. Of course, I'm not going to have time to go into the proof, but I want to talk now quickly about the solution concept that comes out of this. So a minute ago, we had these things, these limiting functions v and w. So I'm going to call those things subjective value functions, okay? And they're indexed both by the player and by the joint policy that is used when you're doing the learning. So a note is that these things can be characterized as the fixed points of a certain operator. And the operator is a Bellman operator, but it's not the Bellman operator that you would expect it to be. It's kind of defined in a sort of unusual way because player I might be facing a POMDP instead of an MDP. Okay. However, instead of thinking about it as the fixed point of an operator, it's probably best to just think of it as this is what my learning iterates will converge to if I run learning algorithm. Okay. So that's what V and W kind of are. So now that I know that these things are indexed both by player and by policy, I can collect these things into two families of functions. Okay, so calligraphic V star is all of those V functions to which the J's limit, and calligraphic W star is all the W functions to which my Q estimates, converge. And jointly, I'll call this VW pair the subjective function family for my game. So once you give me a game and you give me a subjective function family, I can define this thing that we call subjective best responding, and it's going to have the name of the subjective function family kind of in there. Basically, this thing involves an inequality where I say, hey, what is my perceived state value function? What is my perceived action value function? Given my policy, am I doing within epsilon of the best cost I could hope to do, given my beliefs? Okay, and this definition comes from an analogy to MDPs and an epsilon optimality criteria there. Okay, so for a given player, for a given counter policy, I'm going to define the set of subjective epsilon best responses. I'm going to denote it this way, and it's going to be a possibly empty subset of my set of stationary policies. So is that good? I should probably pause here for a second just so this digests. Okay, great. So out of a notion of best responding, you can create a notion of equilibrium. And in this case, my notion of subjective equilibrium is just going to be where all players are best responding with respect to each other, subjectively best responding to each other simultaneously. And so this is basically in direct analogy to Markov perfect equilibrium in Markov games. In that case, you replace V and W by the true cost and the action value function. Okay. That's the definition. I'll use subjective subscript epsilon to denote the set of these things for a given subjective function family. Maybe I'll move on. So the definition's still on here. Why do I propose this notion of equilibrium? Well, basically, if players really think that they're facing an MDP and they really think that this is their value function and this is their action value function, then this actually corresponds to what they believe epsilon optimality to mean. If they then use one of these win, stay, lose, shift algorithms, then it makes sense that this would be where play gets stuck. Anywhere else, some player thinks that he could do better and he'll change his policy. Okay. And the third and important point here is that here, objective functions that can't be verified aren't part of the solution concept's definition. Instead, the solution concept is built around a learning algorithm rather than learning algorithms, trying to find it and it being divorced from learning. So now that I've introduced some new solution concept, I should probably prove that it actually exists, at least in some cases. And the second one, I guess, is the more important, more interesting one. And that says, if a partially observed n-player mean field game has this soft policy assumption I mentioned earlier, and epsilon is positive, and furthermore, if the game has mean field observability, then there exists some subjective epsilon equilibria. The reason I had to show you all those results earlier about MDPs and the existence of perfect equilibrium is because the easiest way to prove this in the case of mean field observability is to say, hey, there are Markov perfect equilibrium in mean field games with mean field observability. And so if you approximate that, the resulting thing will be a subjective equilibrium. So hopefully later we prove that these things also exist for compressed observability and local observability. But at this point, the interesting result is that it exists with mean field observability. Okay. So in the last few minutes here, I'm going to try to connect this back to that picture of policy revision. So now that we know what happens in the subjective universe when players learn and assess with a faulty system model, we can talk about what happens when they plug these learning estimates into the revision step of their algorithm. So in principle, all we're going to do is we're going to operate a win, stay, lose, shift algorithm with these subjective learning iterates. You're going to fix a policy. You're going to run this Q learning and so-called J learning process. And then we're going to check if we're epsilon best responding subjectively with respect to these learned iterates. If we're happy, we stay. If we're not, we'll choose something else. So here's some pseudocode for the algorithm. The blue part is just setting parameters. Don't worry about that. The loop here is this picture. So each cycle here is one iteration of the loop. So for each K, fix your policy, play with that for a bunch of periods, check if you're happy, update your policy accordingly. Okay? Give you 2 seconds to look at this. Now, if you want to see all the details, this is what it looks like. This is obviously unreadable in 2 seconds. So I'll go back to the small picture. And let's get rid of that color and add some new color. The green suite here says check if you are subjectively best responding, but replace the V and the Q by your estimates of those things. Okay. So if I'm satisfying the analogous inequality with my estimates, then I'm going to choose to stay with my old policy. On the other hand, if it looks like I could achieve a better cost, then I'm going to do something different. I've written something simple here, but basically with positive probability, just sample a random policy. So to analyze this algorithm, I'm going to say that if all the players choose their parameters accordingly, whatever that means, then eventually this thing will arrive at a subjective epsilon equilibrium with high probability. So that's the kind of guarantee that we're going to give in our theorem. Parameter selection in this case kind of means that you learn with your policies for a sufficiently long time that your estimates converge to their limits. And then there's a few other things here also. So I'll give you an abridged version of one of our theorems, which says that, this assumption about soft policies giving rise to an irreducible aperiodic Markov chain holds. Some stuff about the policy subset that we're actually going to consider. So it should be a quantized, a discretized subset of all my stationary policies. It should contain a subjective equilibrium. But then you run this algorithm, and if your learning phases are sufficiently long, then yeah, eventually we're going to bump into one of these subjective equilibrium with very high probability, and then we'll stay there. So I'll quickly say a word about the proof, and then I'll wrap up. But basically, if these learning phases are really long, then my subjective value functions will converge to their limits. So my estimates will converge to the subjective value functions rather. And then we can study the policy dynamics instead of with estimates. Why don't we just study a corresponding process where an oracle just comes down and tells me what my V function is and what my W function is. Okay, so I'm going to approximate this oracle process by the process where I answer the same questions involving these learned iterates. Now, the oracle process looks like this. If I am subjectively best responding, stay. If I am not, do something different. It's a very simple process. Does this process always go to subjective epsilon equilibrium? The answer turns out to be yes, but it takes some work to prove it. And at the beginning of this talk, I mentioned some work we did on Markov games, symmetric Markov games. And so the mechanism that we came up with to make this proof go was something that we called satisficing paths. And it has to do with, it's like a generalization of best response paths that shows up in the analysis of randomized algorithms like this. So if you're interested in that, we published this last year. All right. Matthew, do I have 2 more minutes? Okay. Yeah, sorry for running a little long. So starting our conclusion, basically, I was interested in out of equilibrium learning that starts out of equilibrium and in which players adjust their policies. I was especially interested in independent learners and learners that used win, stay, lose, shift policy revision. We did a whole bunch of stuff, and unfortunately, this leads to a rather meandering path. But in summary of what we did, we studied when it's appropriate to take player I's stochastic control problem and treat it like an MDP, and when it is only going to be appropriate to treat it like a POMDP. Building on that, we showed that there exists perfect equilibrium when the game admits mean field observability, full stop. So finally, many players, real perfect equilibrium exists as long as the game has mean field observability. We used that and some results from the POMDP theory of the last few years to study the convergence of subjective learning. Okay, these learning iterates where you treat your problem like an MDP, and we found actually these converge a lot of the time. At the beginning, we didn't say whether this was appropriate in every case, but we said if players were to do this, their iterates converge, and we can define subjective equilibrium, a new solution concept that kind of puts learning in the middle rather than on the outside of the definition. After that, we said what would happen if players iteratively change their policies in response to their subjective value iterates. And we found that, yeah, we'll bump into these subjective equilibria. So at the beginning, I said I'm going to try to convince you of 2 things. The first was this thing, facetious comment that said, you should write x mu a instead of x a mu. And the setting of partially observed n-player Markov games, it's because xt mu t is going to be your state, at least under mean field observability. Okay, so the mu t shouldn't be an afterthought. This doesn't just tell you what MDP you're facing. This is in fact, at least when mu t evolves randomly, this is going to be a core part of your information. The second thing, though, and I'll finish with just a slide or 2 about the second point, is that when you start in disequilibrium and then you iteratively revise your policies, you might arrive at something that is surprising. You might arrive at the subjective equilibrium. Okay, but critically, there was nothing about symmetry in our definition of subjective equilibrium. In principle, these things can be asymmetric. And also, we found that empirically, these things end up being asymmetric. So we cooked up a small example. We stylized it as being a decision-making in an epidemic. So we'll have 20 agents in this simulation just for a small, a number that we can work with. Each agent will either be in bad health, in medium health, or in good health. And each agent has the option between going about their business, staying at home, doing nothing, or going to a hospital and getting healthcare. Each player will only observe its own health as well as some signal by like a health, maybe the government will tell you a lot of people are sick right now or not a lot of people are sick right now. And then there's some cost function and transition kernel. So the observation channel basically just says that if 35% of the population is sick, then I'll tell you the signal is high, and otherwise, if less than 35% are sick, I'll tell you no, the signal is low. The cost function is defined in terms of penalties. So there is a reward for going about your business. There is a penalty for being in bad health. And then, maybe this is America, there's a penalty for going to get healthcare because you have to pay for it or something. The transition kernel is a little bit involved, so I'll just tell you about it at a high level. But if you choose action wait, then basically in the next period, your health stays the same. If you choose action heal, then with some probability, you're going to go to good health. And then if you choose action go, well, then there is some probability that your health is going to degrade and you're going to get sick. But the probability of getting sick will increase with the number of sick agents in the population. So this is a game with, excuse me. So this is a game with partial observability. It's compressed observability. And so we ran our algorithm, that Wednesday loose shift algorithm on this game. And we found that quite quickly, at least in this game, you have subjective equilibrium like pretty high proportion of the time. And we probably could have run this longer, and I suspect that it would have continued to increase. But this is more meant to be an illustration than anything else, a proof of concept, if you will. But that's not the interesting part. The fact that it converged to subjective equilibrium, we knew that was going to happen from the theorem. The more interesting part is going to be whether all players end up using the same policy or not. So when we were designing this game, we wanted to basically encourage some kind of splitting behavior. If I'm in bad health, I want to force players to go get healthcare. If I'm in good health, I kind of expect that players will really benefit from the reward of going about their business. And then the splitting behavior we wanted to encourage in the design of this simulation was if you are in medium health, then make your decision depend on the signal. So if a lot of people are sick, you should stay. If not that many people are sick, you should go about your business. I was expecting that all agents would follow this so-called sensible policy during the simulation. But what we actually found was that a lot of people end up being subjectively satisfied, so they think they're happy, but only about 3/4 of agents were using this policy that I expected everybody to use. So what this means is that 1/4 of agents were using some different policy. And so there was heterogeneity in the thing that they converged to. And I guess that's the punchline here, is that through this like policy revision cycle with subjective learning iterates, you can get to asymmetric outcomes. And yet these asymmetric outcomes will be stable because everybody thinks that they're happy. So here are the works that we talked about in this presentation. Hopefully this one stops being an archive paper soon. But yeah, that kind of does it for the meat of the talk. I'm happy to take any questions. Thank you for your attention.
Thank you very much, Bora. We are a bit over time, but are there any questions?
Yes, if you have some time, I can ask
Yeah, sure.
Thank you, Bora, for the very nice talk. So I guess I have a question. I have a lot of questions, but okay. What I understand is that you have an n-player midfield game, and you are trying to look at situation and observability when the learning is an MDP. And you say, if you have global observability, learning is always an MVP. If you have mean-field observability, you need to add symmetry such that learning becomes an MDP. And if you have anything that is compressed or local observability, you don't have learning as an MDP.
In general, that's correct.
Okay. So my question is, my first question is, why don't you need symmetry when you have global observability? Why is global observability enough? And then at mean-field observability, symmetry is now required.
That's a great question. And the answer is basically because with global observability, we will no longer be relying on the connection to mean field games, but rather we'll be relying on the connection to Markov games. And so the structure that we inherit, once it's globally observable, now I get to see what everybody's local state is. And so the conditional probability of tomorrow's global state will depend on everybody's action and everybody's local states, right? So because I get to see everybody's local state and everybody's function, there's an important thing there is that everybody's also using stationary policies under global observability. I don't know if I made that clear during the talk, but if everybody's using a stationary policy during global observability, then I get to see the thing that they're conditioning their action choice on. So their action choice now will kind of get taken care of if I was to include conditioning on their action in the analysis. So in the case of global observability, it is the reduction of the problem to a Markov game that explains why player I faces an MVP. It stops being, we stop needing mean field theory at that point. Maybe I'll go back to I think the second part of your question was in the case of, I'll try to find this theorem.
No, that was it. That's fine.
Okay.